start the recording. So I'm recording this already. Okay, so module 17. This is, we're getting into what's called the inferential statistics portion of the class, where we're going to start to create processes and equations, and we're going to start visiting equations that will help us infer a decision or infer a conclusion for a bigger population from a smaller set of data, from a smaller sample. Okay? So let me go through the entire process of how statistics is done. Okay? And the way that happens, I think everybody remembers this picture, right?
Mm-hmm. Been shoving our face the entire time.
The population, right? We want to answer a question from our population.
They will get it. It's about, is it gonna,
right?
Hey, Ruben, can you mute your mic? We can hear you talking.
Who is it?
It's Ruben's talking to his mom or something.
Oh. Hold on.
Okay,
Let me-
telling him.
Is it Ruben's?
Is
That it? Yay. Okay. Okay, so we want to answer a question from the big population, right? So here's our question. Here's where our question comes from, right? Now, it might be prohibitively difficult to find the answer to this question for the entire population, right? So what we do instead is we grab our question and we produce a smaller sample, right? And from this smaller sample, we ask the same question that we would ask over here, right? Once that's done, here is where we make our conclusions, right? Bad choice of pen. Here's where we make our conclusions of small samples, right? We look at the information that's been given in here, and we try to conclude something for those small samples. And depending on how well we chose this group over here, right, it's probably a good indicator of the answer to our original question from the very get-go. So this is what I'm saying, it's inferential statistics. We are producing an answer from here, and that same conclusion, we infer that same conclusion for the bigger population. Okay? And that's the basic idea.
What does that say? I can't read it.
Conclusion of small samples?
Samples?
Yep. Or from some, it's supposed to be from. Okay? So it all comes down to this. We have a question for the big group. We use a little group to answer it. And if we did everything right, the same answer for the small group is the same answer for the big group. Hence the reason why we call it inferential statistics. We infer. Got it? So the activity I made you guys do before we went off to spring break, right? I broke you guys up into smaller little groups a bunch of times. And I think it was groups of 10. No, 7 or 8, okay? And I made you guys all within your groups find out how many people have cats, right? And I went ahead and every time we got back together, I made a table of all the groups, right? So one of them, so one time you guys broke up, there was a group with no cats. The next time there was a group with 5 cats, right? The next time there was a group with 3, of 2, of 3, of 2, so on and so forth, right? I grabbed these percents and I stuck them on a dot plot, right? And the dot plot themselves, they were these three, and that one, right? Notice what happened with the dot plots, right? Zoom was breaking you guys up randomly. Zoom was breaking you guys up randomly. And the numbers that you guys were getting, right, were essentially from random groups from the class, right? But no matter what, the numbers for our group started to settle above one particular value. Does that make sense? So at the end, we sort of guessed, that's where we got our guess from, this thing right here. Just by looking at the distribution of our smaller samples, when I made you guys break out into the smaller groups, just by looking at those smaller samples, we guessed that it'd be somewhere between 30 and 40%, right? And if you look at the numbers over here, they do bounce between 28 and 38%. So we were thinking about 35% was the actual number that we were supposed to get, right? Still, the 35% was still a guess, right? But it was a sound guess. It was because the majority of the data fell right there in that middle portion, right above 30, 35, 40%, right? And then at the very end, I actually asked everybody how many of you guys did actually have cats. And we got our number being this right here. So the day that I did this activity, 31% of you, so 5 out of 16, actually had cats, right? Which was pretty darn close to our yes. Make sense? And I know this is a small example for what I wanted to show you guys, but it still has everything that is required sort of for statistics. So what ended up happening, right, is I split you guys up into small groups, made you guys get percentages for yourselves about who owns a cat, right? And these all right here were for smaller groups. And we plotted points on them, for them, right? We took an educated guess based on where most of the samples congregated. And that guess was this, actual number was this. So we made the guess, and it turned out to be not too far off. That's what I mean by inferential statistics. So these smaller groups represented the bigger group, right? And this is where I sort of presented this thing called the law of large numbers. So you guys remember what's the probability of flipping heads or tails for a coin?
50%.
It's 50%, right? Are we guaranteed that the next flip would be heads or tails specifically?
Mm-hmm.
We weren't, right? We were not guaranteed that the next flip would be either heads or tails. But what we were guaranteed is after a long time, right? After we flipped it 1,000, a billion, a gazillion times, half of them would be heads and half of them would be tails, about. Right? And that's essentially one of the things that statistics banks on. It's this thing right here, the law of large numbers. So the law of large numbers states that as you do it infinitely many times, right, there's going to be a specific value where the probability will actually lie. So taking into account, so if we go back to our example for the coins, if we flip the coin infinitely many times, we are guaranteed after a long time that 50-50 split, right? So same thing happens with, now that was just flipping, that was just with flipping a coin, right? Here is exactly the same thing. If I would have kept going with this process, splitting you guys up into groups of 7 or 8, I kept on splitting you guys up over and over and over again, right? We're going to keep getting numbers like this. However, they would all start to sit around a specific area, right? And that's what statistics is banking on, that they all sit over a specific area. So that's what this activity was supposed to do. Did everybody get that feeling from the activity?
Mm-hmm.
I hope so.
No.
Okay. Huh? Okay, so let me start with this. What did each dot represent? So we have enough here. What did each one of the dots up here represent? So this dot represented something, this one represented something, this one represented something. What did each dot represent?
If you had a cabinet.
Close.
A group's result of like the question. So like the fractions on the side that you showed us. So the end result of asking each group
Right. How big was each group?
is 7 or 8.
Right. It was 1. It was one sample of 7 or 8 students, right? Depending on how big it came from, right? Does that make sense?
Yeah.
Let's describe the distribution that we get. So what's the shape of it?
Symmetric.
Okay. The center? Where do we think the center is? About?
Around 35.
Around 35, right? And what's the spread look like?
0 to like 0.62 or 3, I guess.
Yeah, how big was that one? 62, right. So from 0 to 62.5% about. Does that make sense? Okay, so now, what is our mean and what's our standard deviation? So I know we have the data over at the right, but I kind of want to get a feeling for it. What do you guys think the standard deviation is about? Or what's the mean supposed to be? Let's start there.
0.35.
The 0.35, right? The 35%. And what does the standard deviation look like? Just ballpark it, eyeball it.
It's probably like 0.2 or something like that with outliers.
So you're thinking 0.2?
Maybe. Probably a little bit less than that.
Okay, we're thinking maybe 0.1 or
Yeah.
0.15?
0.15.
Yeah.
So let's say 15%, right? You know, I'm not trying to get exact numbers here, right? What are the typical sample proportions in this distribution, and why do you think so? So where did the typical sample fall?
Like a little bit less than 0.3, a little bit less than 0.4.
Right, so let's say like 28 to 38 about, right? I need to practice on my 8s. There you go. 28 to 38%, which is about right because look at our data, right? We had 20, nearly all of them, right, were between 28 to 38%, right? Okay. What sample proportions were unlikely? Which ones were unlikely to happen on a regular basis? Looking at our table looking at our histogram or our dot plot from above.
The 62 and the 0.
Right. So each one of those only happened once, right? So those are very unlikely to happen. Let's see. So this we actually found out, right? So our guess is the answer for this one. It's about 35%, right? And how did we determine the accuracy of our guess?
You got the actual number with the whole population.
Right. How about we didn't have it? How about this was, so I know I had this here. This right here. What if we didn't have the actual number? How would we sort of justify our guess?
Could you take the mean of the answers that we
You
got?
could. You could. Do it by eyeball.
That's where a majority of the information falls.
Right. That's as simple as that, right? The majority lied around the 35%. Right? That's how we made our really good educated guess. So then I finally found the answer, right? For everybody. The actual was about 31.5%, I think it said, right? Let me go back up. 31.2%. The actual was 31.2%. Got it? So it turned out that between our guess and our actual, we weren't actually that too far off. Got it?
What does number 9 say? I can't read that.
Majority lied around.
What was the answer to number 8? I missed that one. Oh,
It was our guess. Our
Okay,
guess
the
of
guess.
the 35%. Yeah.
All right, cool.
So Julio, I have a question.
Yeah.
How do you know, like, when you're using a small, so if I'm saying like in the context of our project that we're gonna do, if
Yeah.
we get a sample of like, when in this case we had 16 people,
Yeah.
how do you know if that's gonna be like how do you know it's gonna be a big enough small sample? Like what's too small of a sample?
And what's too big of a sample?
Yeah.
Well, there's nothing about being too big. There is something about being too small. However, when you guys start doing your projects, there's going to come a point where you need to make conclusions for your data, right? It's in that portion where you can spell out that your sample size was not big enough.
Okay.
Does that make sense? So that entails, so basically what that basically is statistical ethics, right? If you do a study and you create a conclusion and the numbers and everything that you know of the process still states that your sample size isn't big enough, right?
Mhm.
Then part of your project should be saying my sample size isn't big enough. So these are the conclusions, but take them with a grain of salt.
Okay. So are we
Does that make
able,
sense?
if we do a poll on social media and we get like 20 people to reply, and then we
Mhm.
take those 20 replies and put them in like groups of 6, and you just randomize the groups every time, kind of like what we did, would that be efficient enough?
So
Does that make sense? Like, do you see what
yeah,
I'm
yeah. So I think so. You're grabbing one data point, or sorry, you're grabbing 20 people, right?
saying?
That is, I think you're getting into the process, and we're not quite there yet.
Okay.
Does that make sense?
Yeah.
Your 20 people would actually be just one sample, and you're going to be basing that one sample off of another number that's going to be sort of like an answer for the global,
Got it.
for the
Okay.
population. Does
Mhm.
that make sense? So in the case that I did, I treated each one of the samples and the global being the classroom.
Okay.
Does that make sense?
Yeah.
But as an extension, right? The population is going to be everybody, right? And your samples are going to be sort of like strict subsets of them.
Okay. Okay.
I mean, that's the difference between the two, the example that I gave out just now and what's actually done in real life.
Okay.
Does that make sense?
Yeah.
We'll get through. Like I said, you were digging into process, and we're not there yet.
Okay.
Okay. So
We didn't finish number 11.
what did number 11 say? Is it one of those like, what did you learn about blah 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 blah?
Said how much error was there in our
How
estimate?
much error is in the? There's not much. That's all.
About like
So what is
12%.
it?
About tree fitting?
3.8?
About tree fitting, yeah. Say it again, Leon.
Would it be 3.8?
Yeah,
How you do that?
about 2.8 is about the difference between them. The point behind it is, it's not much, right?
Mm-hmm. Okay.
Okay, so to demonstrate what the heck I mean, right? A little more. I'm going to do a sampling distribution, okay, for a population proportion. This is sort of like, I know this might sound a little contrived, or a little, let me say, unnatural, sort of, right? Inorganic in this case. But the idea is still there, right? So let me explain our scenario here, right? According to the 2010 U.S. Census, which, by the way, the census is already out. Please fill it out. According to the U.S. Census, 54% of California residents were born in California. Got it?
Mhm.
Okay. To see if what is true for LMC students, right? We're going to ask, were you born in California, right? Our hypothesis is that the 54% of LMC students were born in California. Make sense? We are going to try to find out the actual number of people at LMC that were born in California. That makes sense? The way we're going to do that is by a simulation. So let me switch to this screen. So here we go. So let me, 5. Isn't this all boring?
And
Yeah.
just cancel class.
Time to go home.
Time to go home? No, not yet. What I want to do is this. Let me see. I want to copy this. I'm gonna put it over here. Okay, so let me go back to here really quick. So I want to show you guys what the heck this is all about. Okay, so there are only two responses for the question, right? Are you born in California? That's the question that we're going to ask everybody, right? There's going to be only two responses to that question, a yes or a no. Is everybody seeing my screen? Yeah. Does that make sense? The only difference here is this right here. We're going to assume that, that the percentage of the population that we think is born in California is that 54%. Make sense? And what I want to do, I'm going to be changing this around a lot. Okay? So this is going to be our sample size. How many people from our population we're going to be picking out and asking this question right here. Does that make sense? Whoa. Okay. So we already answered a couple things here. Whoa. Are people annotating? Is that people drawing on my screen?
Mhm.
Yep. People were drawing on my screen.
You can do that?
Yeah, with the annotate button.
Oh, damn. Is that on the phone version?
Yeah, even on the
Oh.
phone version. I tried it out myself.
Let me find that real fast.
I found it.
Yeah, I was
Oh,
gonna say
crap.
you could do it on your computer too.
Yeah,
Yeah.
It's easy to find it.
Yeah. Okay. So the hypothesis, look at that.
I found it.
No, really. I should have never told you guys.
You opened up the
Oh, there's this
Pandora's
one
box.
video.
I know. I opened up Pandora's box, right?
There's one video of this professor who
Yeah.
like let the students write on the screen, and it did
Yeah.
not end well.
So the hypothesis, how is it represented in the graph of the population? It's the arrow. And we already discussed, so 0 is a no, and 1 is the yes, right? So let's see. Portion of students of this. I'm reading to make sure that I'm going to answer the questions that are coming up. Mm-hmm. Wait, what? Ah, okay. I see. I see. I remember this. Okay. So let me go back to this page right here. So I'm going to change this to 10. So I'm saying here that my sample size is 10. I'm picking 10 people out from the population and asking them all, were you born in California? Make sense? And I'm just going to do it one time, and I want everybody to see what's happening. So it's asking 2, 3, 4, 5, 6, 7, 8, 9, 10. So it asked 10 people, were you born in California? And it spat out one little block at the very bottom. Did everybody see that?
Mm-hmm.
Okay. So it just so happens that that one block, right, is the average of the yeses and nos for the sample. So let me copy that. Let me go back to here. I'm going to put it over here. So what we have here, right? Years. So we're still asking the same question. Are you born in California, right? There were 5 yeses and 5 nos, right? So that means that the proportion for the people that said yes and no, that the proportion of people that said yes is that box down here. This is the 50% for the sample. Make sense? So what we're going to do now is on your guys' table, there should be one little box right here. You guys got it? Okay. So this one sample, so we've already done A and we've already done B. So this one sample represents one sample of 10 people. Got it? How far does it deviate from the actual percentage already?
Like 0.04.
4%.
Right. So 0.04 or 4%. Does that make sense?
Mm-hmm.
I'm now going to choose a second random sample. So I'm going to go back to this thing, right? I'm going to choose another 10 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got it? So I'm going to copy this thing. I'm going to put that into our notes. I'm going to put it below. So now our little box here, right? So for 2, we had 1 box. For 3, we'll have a dot here, and our new dot shows up at
7%.
at around 70%, right? Does that make sense? So here, there were 3 no's and 7 yeses, right? Hence the 70%. So now we're going to have, let's go back to number 3. We'll have another dot right here. You guys see where the 2 dots are?
Mm-hmm.
Right?
Those are more rectangles, but okay.
Yeah, more rectangle, yeah. Semantics at this point, come on. So now I'm going to go back. I'm going to do it again. One more time. And again, we got another sample of, how many was it this time? Oh, we got it. The same thing again. So
Why did it
let
change?
me,
I mean, the mean change.
huh?
Did the mean change?
Yeah, the mean changed. So we ended up getting this graph right here, basically, times 2. Make sense? So we're going to do it again. We have 1 dot at 0.5 and now 2 dots at 0.7. Does that make sense? I'm sort of rushing this because it's really, really boring. I want to jump to 5 because I think you guys are getting the point behind it. Let me jump back over here. So we've only done 3 samples, right?
Right.
Let's say I do 5 more. Where do you guys think those new samples should land?
Near the 0.5.
Close. Real close. What were we projecting for the whole entire state of California?
54%.
The 54%. Does that make sense? So we're thinking, right, that if we just start asking this at LMC, it should start falling around that 54%. Correct? So I'm going to do 5 more. So now it's going to do 5 samples of 10 people. So how many people did I ask by doing this?
50.
50, exactly. So there's 5 samples. Each one has 10 people. So it's got to be 50 people, right? There we go. What kind of distribution do we have? What does it look like?
Pretty even.
Will it be uniform?
Yeah. Well, hold on. Let me do A first.
Normal.
So we were hypothesizing that there would be about 50%, right? It should be pretty close to around the 54%, right? So we guessed about 50%. How many random samples have we collected?
What, 80 because you did 5 more?
Exactly. So this is 80 responses, right? And how did that break up? It was 8 samples, right? Of 10 people each, right? So what's that blue line tell us about our data?
That's where like all of it falls in between. The majority of it falls in
Right. So
between.
it turns out it gives you sort of like the typical values. You guys remember that, the typical values?
Mm-hmm.
That's exactly what it's doing, typical values. Okay, now let's go back to this thing. I've got a button there that says to do it 1,000 times. So I'm
Do
going
it.
to ask you guys again. Most of these responses, where should they be falling around?
5-4.
5-4.
Yeah, the 0.54, the 54%, right? I'm going to go ahead and hit it.
Yep.
Oh, okay, cool. I thought it was going to make us watch it.
Oh,
Yeah,
heck no. Oh, God, no.
that would have been fun.
Yeah, that would have been, yeah.
You should have just canceled
Imagine,
class at that point.
yeah, I know. I would have just canceled class there. Thank God it didn't animate it. But there it is.
So why did it go to 1,008?
Huh?
Number of samples?
Yeah.
He just
So-
did
We did.
1,000 more.
Yeah, he did 1,000 more. We did 8 before, then
Did
he
8,
did
yeah.
1,000.
Yeah, I did before. Yeah, I did 8 before, and now I did an entire 1,000.
Okay.
Mad Lad did it.
All at once. Super quick. Snapping my fingers. So notice what happened, right? where were we expecting all those values to land?
Before.
Right, the 54%. Make sense? And lo and behold, that's exactly what happened. Now, there's a picture here, right?
Mhm.
It is not exactly the same as the one that we just saw from here, right? So that table is not, or that chart is not anywhere close to what we have here, right? But it is not far off. The idea here is the computer itself, this is the thing that feels unnatural, right? Because you would want to be able to see this. The computer did it randomly. So all of these, all of those samples that it did, all 1,000 of them, you can assume that the computer did them randomly. Yet, if you look at the distribution of how those sample proportions sort of doled themselves out over a number line, they all started hanging around exactly where we would hope they'd be, around that 0.54. And like I said, that is exactly what we're banking on as statisticians. Okay, so how many random samples did we collect? 1,008. How many in each sample? Those are 10 of them, right?
More
Describe
than
the shape of the
people at
distribution.
home see.
What kind of shape do we have?
Normal.
Normal. What is the mean of the sampling now? Let's go back over here. The mean,
53.5, so 54%.
53, right, 54%, just about, right? So 53.57 is actual, right? Make sense? So now, what I want to do is this. Here, the average was 0.5, right? And we did it again. The average was 0.6, right? Oh, that's what I didn't do. I didn't take a picture of the third sample when we did a 8, but the average was, I think, 0.56 there, right?
Mm-hmm.
And then if we, now that we jumped all the way down to 1,000, right? Look at where the average fell. Make sense? So how much error is there between the between the 0.54 and the 0.5357? That's less than 1% error, correct?
Yeah.
So what are the interval of typical measurements? Let's see, where did they typically land?
Like 4 to 0.7.
Yeah, maybe 0.39 to 0.7. Let's just do 0.4 to 0.7, right? Well, 40% to 70%. Okay. What kind of proportions were unusual in our experiment?
Like anything above 70% or below 20%.
Right, so there were these 3 over
101%.
here, and maybe these couple over here, right? So it's at 80, 90, 100%, and 10, 20, 30, right? Oh, and 70. And then 0, 10, 20%. So notice that the majority of them, right, landed here, right? And if they landed outside, those are considered unusual, correct?
Mm-hmm.
And it turns out these over here, these are what we're going to be using sort of repeatedly. It's good that you guys can identify that these are unusual, okay? These are the ones that we're going to be using repeatedly to prove and disprove certain findings.
So anything outside of the typical value is unusual?
For now.
Okay.
For now. So the reason why I say for now is because there is going to be a method to quantify what we will consider as unusual. Does that make sense?
Like an outlier, right?
Yeah. So right now I've just told you guys sort of like the argument that I've been using for now has been, you know, these, because they happen so often, right? These are usual, right? And these out here, they're unusual because they happen not too often. Does that make sense?
Yeah.
And so there's no quantification there. There's just basically just sort of off my gut, right? Saying these are usual, these are not unusual. These are usual, these are unusual, right? There's going to be a way that we can determine using numbers how we will find out if something is usual, unusual, so on and so forth. Does that make sense? Hopefully I didn't completely sort of word vomit there. At least not entirely. Okay. Let me read this. Okay, yeah. I am going to skip number 7 because that actually requires us to be in class. Okay. So let me go to 17.3. So today is going to be actually, you know what? I haven't given you guys a break, have I?
Nope.
Nope.
You guys are probably tired of talking to me. Go ahead, take 10 minutes so I can review some stuff here.
Well, if you insist.
If I insist.
Regular.
She got an appointment with her counselor today. Her, what is it, operation counselor. She seemed to like the lady.
No, but I wouldn't take the mouse. That's two different ones?
No, it's one.
Oh, it's not that one?
It's not. This is the wireless one. Somebody outside.
Oh,
I hear
it's a
baby.
nice day out.
Yeah. I would have stayed outside, but the sun was pounding just now. There's not a cloud in the sky.
Good. It's been cloudy, rainy all week.
Oh.
Weekend, I should say.
Mm-hmm. Did people have uh what's this thing called, a like a spring break to-do list? Yes, no,
No.
Not really.
no,
My spring
not
break
really.
to-do list was go to work 5 days.
And then
So
come
that's
back.
fine, pretty much.
Yeah. Usually I have something to do. Like I'd say like, oh, spring break. I'll do this, 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 and this. And this time around I had one thing to do, and that was clean my backyard. And I did that already. That happened on Thursday. And that was it. And besides that, I've been watching movie upon movie, playing video games here and there, and then grading.
Sounds like about everyone right now.
Yeah.
Except replace grading with homework.
Yeah, exactly. Yeah. We've just been watching stuff on Netflix and Hulu. I binged Tiger King in a day.
Yeah, that
Watched
show
that
was
yet?
that show's weird. I haven't seen the whole thing, but just off of the one episode, you're just like, this guy's crazy.
Yeah. And then the other one that we've been watching like slowly now is the one Dirty Money on Netflix. Like if you really want to get pissed off at the world, Dirty Money's the one to do it.
There was that one, and then the Making a Murderer show.
Oh, I never watched that one yet.
That one was frustrating to watch
Really? Wow.
because it's just like it's about like a guy getting basically told that he murdered someone when he didn't. And the cops kind of like forced it upon him, kind of deal.
Oh, I've heard of those. Wow.
That one just
Yeah.
clenched fist the entire time you're watching it. It's
Yeah.
like, how does this happen?
How does this happen? Yeah. Yeah, I remember I remember there was a case back in the day about that one. About a case like that like some guy, he just because I think it was like,
Was it the one that Seinfeld saved the guy that proved he was at a Dodger game the night that someone died that he was
no,
linked in? Okay.
it wasn't that one. There was another one where like it was this like 15-year-old kid, right? The window to his room was facing a big, huge, giant green field of grass, right? Half a mile down, like half a mile across that field, a body was found, right?
Mm-hmm.
And he never saw anybody. But he walked by the spot like over and over and over again just to get to school. So because of those like 2-3 things, right? And the body was like behind like a trench. It's like the kid was able to pass by like left and right from it and not be able to see it because it was behind like shrubs, right? But solely for the fact that the body was in view of his window and he passed by it every day,
Mm-hmm.
they tried to say like, yeah, you did it, right?
Oh my god.
Yeah, exactly. So so that was bad enough. Then I guess it was like the county sheriff was interrogating him, and both the county sheriff and the police were saying like, come on, just fess up, man, you know you did it.
Yeah, you get
Just tell
told
us.
so many times, and then they say it, and it's like, oh, there we go.
Oh, there we go, exactly. So you're, oh my god, yeah,
Yay, psychological manipulation.
right, exactly. So at one point, you just want them to stop saying shit, and you just say, fine, fuck, I did it, leave me the fuck alone. the guy got like, hi there. The guy got like 30 years or something. And when they found out that, like, I think some judge said, like, yeah, this was not supposed to happen. They cleared his name 30 years later, and they gave him like $5,000. That's it, $5,000
Yeah.
for all the time that he spent in jail.
There was
Whoa.
there was that one recently that the guy got awarded like $1 million for being in jail for like 25 years, but that was just what the state had said if they had a wrongful conviction,
Right.
which is like I don't think any kind. I mean, the million's nice, but I don't think any kind of money is gonna help the time lost.
Yeah. Robert Cotton, huh?
Who dat?
Yeah, he was accused for rape and was stuck in jail for like 28 years. And like he got a retrial because there's a semen sample that basically proved it wasn't him, but he still got reconvicted. And like only after like another 10 years did he finally like prove his innocence.
Wow.
Like
Yikes.
the semen sample was from the crime was literally not his.
Yeah.
And there's even a book about it that him and
I
apparently
think that
him
might
and the
be.
woman who accused him are like best friends now or something. Like,
Yeah. Yeah. Dirty, man. Just horrible. All right. You guys ready to keep going? The last 30 minutes of class?
Yes.
All right.
do we need in this last 30 minutes of class?
I know. You actually do.
We do.
This is.
Doing homework is
Huh?
gonna be a bitch.
Yeah.
What if he just didn't assign homework?
Then you would never learn statistics. Yeah, this section right here is. Yeah, this section right here is god awful in terms of showing you guys how to do it without having you guys in the room. It's so much better to do it in person. Because it at least made it a little bit more tangible. Now we're just doing it completely abstract. This is just like an experiment of thought, and those are really, really, really hard to grasp onto.
Yeah. Unless
Yeah.
if the point of it is to make your brain hurt.
Unless
Just to prove a point.
Just to prove a point, yeah.
Yeah.
Unfortunately, I'm not trying to prove a point here. I'm actually trying to show you guys some like really, really neat stuff.
There's this thought experiment. It's like the Infinite Hotel. And the whole point of it is just to show how painful it is for us to imagine infinity.
Yep. The Infinite Hotel is actually like a common mathematical problem. There's a bunch. Oh, I'll leave those for later. There's also the Barber of Seville. I don't know if you guys have heard that, but that one's also trippy. But back to statistics. Okay, so for 17.3, what we're going to deal with is looking at the sample size of a sampling distribution. So up here in module 17.2, this whole time, all of this, right? How big was the sample size?
10.
10.
10. So the sample size was always 10. Whoa. Not what I wanted. The sample size was always 10, right? So what happens if we change that 10?
It'll either get bigger or smaller depending on how we change it.
How so?
Well, if we have 11 or more, it's bigger. 9 or less,
Well,
it's smaller.
What do you mean by bigger?
The sample size.
What's going to get bigger?
The people in the sample.
Well, I'm sorry. Duh, right? What I want to do is look at this down here. So what we're going to be specifically concentrating on is this portion down here, which is what's called our sampling distribution. Does that make sense? This is how our samples distribute, hence sampling distribution, right? So here in this printout right here, the sample size, the number of samples is 10, and the sample size is, or sorry, the sample size is 10, and the number of samples is 10,000, right? If we made the sample size bigger, what do you think will happen to our sampling distribution, this thing down here? So
It'd probably go to the left.
why to the left?
Because the higher the sample size, the probability of it staying at 0.54 decreases. I'm not really sure.
So how about we think this out, right? I think you have a couple good points there. And you're looking at you're looking at the correct stuff. All I'm doing is changing this sample size right here, right? Will the percentage of people living in California that are born in California, will that number change at all?
Nope.
No.
No. So this proportion up here of 0.54, right, shouldn't move. And that's where this thing sits above. Does that make sense? So that middle hump where we're thinking that we're going to get most of our answers, that middle hump is supposed to stay there, right? Am I making sense, or did I break people already?
That makes sense.
Okay.
Mm-hmm.
So it can't. So this thing won't move left, and it won't move right. So those things won't happen. What else do you think will happen? Any guesses?
If you increase the sample size?
If you increase the sample size, right? So how did we use this in our calculations? So we ended up getting, so right here, right, we have 3 no's, right, and 7 yeses, right? Does that make sense?
Mm-hmm.
So then this particular sample would be the 7 divided by 10, which gives us our 70%, right? Make sense?
Yeah.
So then this guy right here should have maybe fallen in here somewhere. Correct?
Okay.
So now, if we made this bigger, what do you guys think happens with this thing down here?
Like the exact location of each bar would change because it's no longer out of 10, so you wouldn't have like a perfect like 10, 20, 30, 40%.
Right, so that 10, right, limited our outcome of this calculation right here. Correct? We were only able to get 10, 20, 30, 40, 50, 60, 70, 80, 90, 100%, right? If we make the 10 bigger, right, then this number over here becomes a little bit more refined, correct? Turns out it does a little bit more than that. Let me move down to the next page, if it ever shows up. There we go. It makes it more refined and it makes it much smaller. So let me show you guys what the heck I'm talking about. I'm going to go back to this thing, right? We've already done 1,000 with of sample size 10, right? So let's make my sample size. How big? How big of a sample size you guys want to go? Let's go 100. Okay. And I'm now going to use. I'm going to do it again, but I'm going to do 1,000. So now my sample sizes are 100 big. So I'm asking 100 different people. Were you born in California? And I'm doing this 1,000 times. And notice what happened to my graph. Do you guys see my graph? Yeah. So describe the difference here. What's happening?
There's more data, specific data.
Right. Specifically, what happened to our distribution? What happened to our bottom thing down here?
It got like more condensed in the middle instead of being spread out.
Right. It got much more condensed. Does that make sense? Specifically, it got much more condensed around what point?
The mean, yeah.
Right. What was our mean?
0.54.
Right. It's this 0.54 that's way up here. Does that make sense? It is this 0.54 way up here. Got it?
Mhm.
So let me go back to this. Right? So that's what happens here as the sample size gets bigger. The sampling distribution the way that our samples distribute becomes smaller. They get more condensed. Got it? So now, here they did a sample of 10 and a sample of 40. Which one is 10 and which one is 40?
The top one is 10. Oh, wait.
What'd you ask?
Yeah, the top one.
Which
would be
one?
The
10,
top one is 10 and
the bottom.
Oh, yeah.
40.
Yeah, top one's done.
Right. So then this one, the sample size is 10. And this one, the sample size is 40. Make sense? Let's compare them. Let's compare the means. What happened to the means?
Nothing.
Nothing.
Nothing, essentially, right? So if we look at
Well,
the
I mean,
means,
there's like that 1 or thousandth decimal place or whatever difference.
right. So they are different, but are they different by a lot?
There's less than 1% of error, right, is what you would say.
Yeah, exactly. So, whoa.
So is it the smaller the standard deviation, the more condensed it'll be?
Say it again.
The smaller the standard deviation from the mean is the more condensed it should be.
Exactly.
Okay.
Yeah. So then now, the standard deviations, here's the good stuff, right? Because how do we measure the spread of a normal distribution? We measure it by using its standard deviation, right? What happened to the standard deviations between the two?
You got cut in half.
Right. So sample size equal 10 is the one for the sample size equal 40, correct?
Mhm.
So the one for 10 is 1584.1584, and the other one 0.0788. right? How does that show on our distributions? How does that show on our graphs themselves?
There are points closer to 0.54 in the 40 than there are in the 10.
Right. So SS, whoops, sample size equal 40 is much more condensed. I should, whoa. Around 0.54, then SS is equal to 10. Does that make sense?
Yeah.
Right? So like I said, that shows in the distributions themselves, right? This one is much more compact in together. This one's a little bit more spread out. Got it? Okay. We're now going to change the context of the situation here. Suppose we think 80% of LMC students will vote in the next election, right? Our hypothesis in this case is that 0.80. Make sense? We are thinking that the population of LMC students that will vote is 80%, okay? We have four distributions here, right? One of them belongs to a sample size of 10, one of 20, one of 50, and one of 100. Let's start by labeling them. Which one's which?
They go in order.
20.
Yep, this one's 10, 20, 50, and last is 100.
Yep.
Right? How did we make that decision?
Got closer together, the standard deviation decreased, I guess.
Right, so
Yeah. Better way of putting it.
as n gets bigger, right? The distribution would tighten up, right? The sampling distribution. Right? And we see that. So 10 is 10, right? But as we get to 20, it condenses, right? As we got to 50, it got tighter together. And as we got to 100, it got even closer together. Does that make sense? What do we notice happens to the means of the distributions? So we're
They
looking
stay
at these.
relatively the same.
Right. The means are all about the same. You guys see that? Why do we think that that's not going to change? Can somebody give me a good reason for why we think those weren't going to move anyway?
Well, because if you have 100 people and like 60 of them are yes, 40 of them are no, regardless of how you group them, it's going to be the same.
Okay.
Like if I take that 100 people, put them into groups of 10, then it'll still total to 60 people yes, 40 people no.
Mm-hmm. Yeah. That's a good point. Give me another one. Oh, whoops, I was looking. Haha.
The law of large numbers.
How so?
It's since they're all a large number of samples, they're all going to even out for the most part.
Right. What was the percentage that we thought?
80.
Yeah, it's the 80, right? That's not going to change at all. Make sense? Same thing with the law of large numbers. We're thinking that the population of LMC, right? Everybody of LMC, 80% of them was going to be voting in the next election, right? That number didn't change. right? So that's why they're supposed to all be the same, right? And same thing like Connor was saying, right? That if it doesn't matter whether we have sort of like 100 or 50, right? Out of the 100, 80% we're going to say yes. It doesn't matter if we split them up into smaller groups, right? Those smaller groups are still going to have about 80 saying yes anyway, right? Okay, what do we see about the standard deviations? So now we're looking at these.
Smaller.
They get smaller, yeah.
Smaller, 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 smaller. Why?
Each time you add a higher sample size, it becomes more refined.
Right. Does that make sense? So instead of dividing by 10, we divide by 100, right? So we can get the 47% or 42% or 79%. Make sense?
Hmm.
So here's a good one. Intuition tells us that larger samples have less error on average. How does the sampling distribution support that? So let's go back up here. How does that statement, how is that statement corroborated by our 4 histograms here? So larger sample sizes have less error.
The more refined info allows you to be more accurate.
Yep. Does that make sense? So as we go down, right, we are dividing by a bigger and bigger number, right? We're getting a bit more refined in terms of what we can calculate, right? But altogether, what's happening? What's happening to our data? It's becoming more condensed around what particular value?
The mean.
The mean, right? Which is in this case, what is the mean for all of these?
80%.
This is at 80%. So both of those things together gives us our answer for D, right? Wow. Today is boring.
Because we gotta study math.
Hmm?
Because we're doing math.
Yeah, it's true. This is actually, you're right. This is math. This is legitimate mathematics here. This is what mathematicians do on a regular basis, actually. Let's see. Which sample size keeps the average error within 10% of our hypothesized 80%. Which ones do it?
10 and 20.
Within 10%. So
Would that be referring to like the standard deviation?
that would be.
Yeah, that's what I
Okay,
thought.
then.
That's why I said 10 and 20.
So it,
So wouldn't it
It-
be everyone except 10? 8%, 5%, 4%.
Yes, sorry. Everyone except 10. You're correct. So within 10%, what is 10% in decimal?
0.1.
0.1. We want it to be less than 0.1. Does that make sense?
Mhm.
So this one does it, this one does it, this one does it, right? This one does not. So it can't be 10 because that, so what's the, for this, for 10, it's keeping it within what percent?
1? Or, wait, what?
For 10, for the sample size 10, it's keeping it
Oh,
between how many
like-
percent?
Like 13 almost.
Almost 13%, right? So yeah, so 10 won't do it, but 20, 50, and 100 would. Got it?
Mhm.
Okay. What do you guys notice in the distributions now?
Yeah, I think
They-
like as n increases, like the distribution condenses.
Right. But what about the shapes of them?
They stay normal.
They stay normal-ish,
They
yeah.
stay normal the whole time. You guys see that? My pen is glitching. My pen. Are you serious?
Yes, extremely so.
I think your pen's trying to sell you something.
Telling
I
you to
know.
cancel
God dang it.
class.
Okay, cancel class. I'm canceling class.
Finally. It's like, what, 2 minutes left?
Exactly.
Can you
All right.
answer 4?
Huh?
Can you answer 4? You don't have to write it out. You just tell us.
Yeah, I could answer 4. That'll round out everything, wouldn't it? So suppose that we pull a random sample of 10 real students, and 70% of them say that they plan to vote in the next election. Do you think that this sample came from a population of 80%? planning to vote, why or why not. So if our sample is 70%, right, from 10 real students, right, which one of these 4 are we going to be using?
The first one.
The first one. The sample size is 10, right? In that one, is it unusual to get a sample like that?
It's typical.
It's a typical one, right? Because it will fall in this box right here, right? Does that make sense? So
And
this is
it
going to
has
be
like a 13% error range, so it's within that 13%.
something like that, yeah. So this is pretty typical, right? That is a pretty typical outcome, right? Does that make sense? Now, let's say instead of a sample size of 10, we have a sample size of 100 now, right? So now, which histogram are we going to use?
The bottom.
Bottom one.
The bottom one, right? Now we're going to use this one down here. In that one, if we get 70 out of 100, is that usual, unusual?
Unusual.
Unusual.
Why?
It falls out of the typical values.
Right, so 70%, let's say it's like right here, right? That is the collective of everybody below 70%, right? Does that make sense? So in this case, right, it'll become unusual. But it's the same value. Whenever my computer starts to, there we go. Come on, populate, populate, populate. There we go. So this one is for this one, it'd be very unusual, right? So there's not many samples below 70%. Does that make sense? Okay. This right here, what I'm showing you guys, is like the basis of what's called hypothesis testing, where we grab a hypothesis, we grab a sample, and depending on how usual or unusual it is, right, it gives us good evidence to determine whether or not our original hypothesis is true or not true. And that in itself is inference. We'll cover more of this on, what day is that? Thursday? Thursday.
So that's why you always want a larger sample size.
Next week, right?
Right, next week, yeah. Yeah, that's why a larger sample size is best, because then you have a much more accurate reading, right? Or much more accurate data point. And depending on that, you know how close you're supposed to be, right? And if you are still far away from what you're supposed to be, then you can say, yep, we're wrong. Does that make sense? More sense?
Yeah, no,
sense?
It's really not as bad as you've made it seem.
It's if you think about it logically, it makes total sense, but it's hard to sort of like grab it and hold on to it and make that idea sort of make sense.
Yeah, it's a different kind of math than most
Huh?
people are probably. It's a different kind of math that most people are used to, probably.
Right. It's a logic problem. That's what it is, and that's what people have. That's what people have most issues with the straight out logic of statistics. It's not difficult, like in terms of putting it down on paper, but in terms of understanding it for the very first time, super hard. Yeah. So we'll cover more of this on Thursday. I know today was super freaking boring. But I hope it wasn't that bad. I
That
did
really wasn't.
at the end cancel class, so we'll be okay.
If it makes you
I'll
feel any
see-
better, I wasn't that bored because I had video games in front of me.
You know what? I
What?
have been gaming a whole lot more now since the shelter in place has gone through.
Because there's not much to do.
There's not much to do, yeah. I mean, and my wife is having the same problem. She's like she would now hers is watching Netflix stuff, so it's been more like, all right, she's binged like 3 movies in a day. She needs to do something else, and
She should just like do a Harry Potter marathon and watch all of them in one sitting.
but then like
That's like
after you
20
do that,
hours.
what do you do? What do you do?
You take a nap for like a whole day.
I mean, but yeah, but
It's
then
gonna take a whole day,
won't-
and then
we-
then you move
we-
on to like Lord of the Rings and The Hobbit, right? In complete sequential order, right?
Oh my
And
God,
then
yeah.
like maybe like John Wick, and then like everything,
But
all the other
yeah,
ones.
but then what though? Then so it'll be her day will comprise of watch a movie, take a nap, watch a movie, work, watch a movie, take a nap, work, watch a movie, take a nap, over and over and over and over again. So yeah. And same thing for me. It's sort of like all I got to do is grade video game, sleep, grade video game, teach.
You don't even
grade video
eat.
game.
Wow,
Yeah, I eat.
the mental fortitude to
I
not
know.
eat.
Yeah. So.
Or use the
Alright.
restroom. Probably has a catheter.
Or that, yeah. Okay, fine. All right, I shall see everybody on Thursday. Thursday.
Yeah, have a
Thursday.
good one.
Repeat
what just
Yeah.
Yep.
Goodbye.
Wait, do you
Later.
have office hours
Wait,
right now?
what?
Huh?
What happened?
Class is over.
What?
Yeah, class is over, yo.
Why? For what purpose?
Because it's 2:50.
Oh, damn.
Are you still in New Jersey?
Yeah.
Let me guess. It can't be.
Did I fuck
Is-
up my time? My time change?
Is it 5:00 over there?
Yeah.
Yeah.
Wait, what time?
I think
is
you
it?
might have fucked up your time.
Dude, what? Alright, never mind. Fuck this. Bye.
Later.
Would you have
Ruby.
office hours right now?
I can't hear you.
Would you have office hours right now?
Yeah, I'll have them in about 15 minutes. I need to go eat something first.
Okay. Yeah, because I
Yeah.
have some questions about the class and need some help with my lab module because I forgot about it and now I have issues trying to actually do it since I forgot all about it, and then now looking back at the questions and all that, I have issues trying to answer those questions.
Okay. Yeah, that's fine. We can answer them during my office hours at what,
Okay.
3:15?
Okay.
Cool.
Is it going to be on the Zoom or the office hours Zoom?
It's going to be the office hours Zoom.
Okay, perfect.
So go to the link where it says office hours on it.
Okay.
Cool.
Yes.
Okay. Go get something to eat, man. Get
Yeah.
well fed. You did good on your test.
Yeah, I saw, but right now I'm doing the modules 17, 18, and 19.
Yeah.
For modules 17 and 18, I had real difficulties with the like about finding out the means, about the portions and everything like that.
Yep.
So
I know.
I'm commissioned
Well,
with that.
Yeah, I think you're reading ahead a little bit, which is not bad. That's actually pretty good. But we're just not there yet. So that's why you're probably looking a little confused. So we'll talk about that during office hours.
Okay, perfect.
Cool. Okay.
Yeah.
I'll see you in a little bit then.
All right.
Okay.
Bye bye.